Oil and gas flowing through pipelines represent the success of a well that's come in. Wells usually contain gas, oil, and water. Water that seeps in and accumulates in the reservoir during the life of a well. As fluids move through the formation, water mixes with oil and gas. Excessive water affects production and revenue, so it must be removed. Production separators are used to separate water from gas and oil. If well fluids are thoroughly mixed, they form an emulsion, and emulsions must be specially treated before the components can be separated. A heater treater, like this one, is used to help break an emulsion. This is the first section of a 3-section module covering emulsions and horizontal heater treater principles. In this section, we will cover emulsions, how they're formed and how they're treated. In an emulsion, one liquid is spread out or dispersed throughout the other in the form of small droplets. In oil field emulsions, water is usually dispersed in oil and is referred to as a water in oil emulsion. Water that readily separates from the oil is referred to as free water. Emulsions are difficult to break because of emulsifying agents. Emulsifying agents are substances that promote the formation and stability of emulsions. By collecting on the surface of water droplets, emulsifying agents form a tough film which keeps the droplets from combining, or coalescing, to form larger droplets, which will settle out by gravity. Depending on the type and amount of emulsifying agent, an emulsion may be described as tight, that is difficult to break, or loose, easy to break. Different emulsifying agents occur naturally in different reservoirs. Agents commonly found in oil field emulsions include asphalt, resins, paraffins, and oil-soluble organic acids. In order to break an emulsion, the film surrounding the droplets must be neutralized or destroyed by using treatment methods. Treating in the field can be done with equipment such as free water knockouts, separators, heater treaters, and electrostatic treaters. Treating also includes adding chemicals to an emulsion immediately after it's produced. Several factors determine how easy or difficult it will be to break an emulsion. Some factors are the type and amount of emulsifying agent and the conditions under which the emulsion was produced. Let's look at some of these factors. Generally, emulsions with a small percentage of water are more difficult to break. Old emulsions die hard. The longer an emulsion remains untreated, the harder it is to break. Increased agitation means greater disbursement of water and increased tightness of the emulsion. Emulsions containing small water droplets are more difficult to break because the small droplets are lighter and will not settle out as easily. This also happens with oil with a low API gravity. The water droplets tend to stay suspended. Oil with a high viscosity, that is, a high resistance to flow, tends to keep water droplets in suspension, making it harder to break the emulsion. Pipeline companies pay for oil and gas, not water. So water must be removed before delivering it to the pipeline. And in most cases, that means some form of treatment. Now, the amount of water in an emulsion may vary from a small fraction of 1% to almost 100%. Generally, older wells produce more water. No two emulsions are alike, and they must be tested frequently because over the life of a well, emulsions change and treatment processes must be changed accordingly. The treatment process must be monitored carefully to ensure maximum yield and minimum loss of product for our company. Treating emulsions may include such processes as utilizing settling time, heat, chemicals, electricity, or mechanical devices. Let's take a closer look at each one of these processes. The time needed to completely separate an emulsion is called settling time. Settling time of a water and oil emulsion is affected by such things as viscosity, size of water droplets, and gravity. I'll create my own emulsion using water and oil, and I'll show you what I mean. First, pour in the oil. Add a little water. Tighten the lid. And shake. Now this is roughly the kind of emulsion which flows from the wellhead. If the oil has a high viscosity, that is, it's thick, then the water droplets cannot move around easily and will not settle out quickly. Settling time is also affected by the size of water droplets. Smaller droplets are lighter and take longer to separate from the oil. If the difference in API gravity between water and oil is small, then separation is slow. However, water weighs more than oil and will eventually settle out if given enough time. Some loose emulsions can be treated adequately through settling alone. Tighter emulsions need additional treatment designed to speed up the settling process. The ideal way to treat an emulsion is without heat, but treatment frequently requires heat to speed up separation. Let me show you what I mean. I'll take another jar and make an emulsion exactly like the first one. Pour in some oil. Add a little water. And tighten the lid. And shake. But with this jar, I'm going to loosen the lid and add some heat, just for demonstration. Now, heat alone will not break an emulsion, but it aids in several ways. Heat causes the water droplets to move around faster, striking each other with greater frequency and force. As the droplets collide, the film of emulsifying agent ruptures and allows the water droplets to combine, forming larger, heavier droplets. These larger droplets yield to the force of gravity and settle out. Heat lowers the viscosity of oil. This allows the water droplets to move through the oil more easily and settle out more quickly. Heat speeds up chemical action. Chemicals make a rigid film around the water droplets. As heat is applied to the emulsion, water droplets expand and break the film. Water droplets can then merge into larger ones and settle out. As you can see, there is a difference. In only a short time, the heated emulsion has separated more than the unheated emulsion. But heat should be applied only when necessary and as little as possible, because too much heat will waste energy and cause greater wear on equipment. Also, excessive heat can burn off the valuable lighter ends of crude oil, changing the oil's gravity and resulting in lost revenue. Another form of treatment is chemical injection. Emulsion-breaking chemicals are injected into the well stream ahead of the heater treater. Chemicals react with the film that surrounds the water droplets. This reaction destroys or neutralizes the film and allows the droplets to combine or coalesce with each other and separate from the oil. There must be sufficient agitation to allow the chemical to come in contact with each water droplet. The amount and type of chemical required directly affects how well the emulsion breaks and the time needed for settling. Warmer emulsions require less chemical. However, too much heat will cause the undesirable effects we mentioned previously. Electricity is also used to separate oil and water. Electricity is generally used in conjunction with heat and chemicals in an electrostatic treater, commonly called a chemoelectric unit. This form of treatment will be discussed in another module. Finally, mechanical devices such as gun barrels and free water knockouts are used to treat emulsions. A gun barrel is a settling tank which separates oil and water in the field. After the emulsion has been heated and treated with chemicals, it's pumped to the gun barrel where water and oil settle out by gravity. Gun barrels are still common, especially in older fields, but they're frequently replaced by heater treaters. A free water knockout is also a gravity-type separator. It removes excessive water from the well fluid before the fluid reaches the treating unit. Sometimes a filter or excelsior, called hay, is used to catch particles of oil that may be entrained in the free water. The free water is drained off, and only emulsion passes on to the treating unit. The free water knockout prevents overloading of the treating vessel and saves fuel. In this first section, we've looked at the basics of emulsions, how they're formed and how they're treated. We discussed some of the factors that determine settling time and how heat speeds up separation. Take some time now to stop the videotape, read section 1 in your student manual, and answer the questions. When you return, we'll look at the design of a typical horizontal heater treater. Take your time, and I'll see you when you're finished. A horizontal heater treater is a pressure vessel which combines all the equipment necessary to treat an emulsion. Sometimes it's referred to as a flow treater or an emulsion treater. Like other treatment equipment, heater treaters are designed to break an emulsion and allow water to settle out, so only clean oil and gas is transferred to pipelines. This is the second section of a 3-section module covering emulsions and horizontal heater treater principles. In this section, we'll go over the design of a typical horizontal heater treater, the basic components, and how they work together in the treating process. Horizontal heater treaters are commonly used where vertical height is limited or if the treater operates under pressure. The heater treater for any given lease is designed to handle the well fluids of that particular lease. But in every case, treating must be carried out at the lowest possible cost with the least addition of heat and smallest loss of oil gravity. The design of a horizontal heater treater may include the following components or sections: an oil and gas separator, free water knockout section, heating section, water wash, filter section, stabilizing section, and heat exchanger. Any number of modifications can be made to the basic design. For example, both the size of the internal sections and the amount of heat required may vary. Another example could be the need for a filter or hay section. Knowing which treater is most efficient for a certain area depends on the climate, amount and type of well fluids to be handled, and the characteristics of the emulsion being treated. Let's take a closer look at the external components of the vessel, and we'll begin to see how this process takes place. The firebox contains a gas burner which provides the heat source for the treater. The stack is a metal cylinder where exhaust gases are vented after flowing through the fire tube. The thermometer shows a pumper the temperature at which the emulsion is being treated. The thermowell provides a location for the thermostat temperature probe, which helps maintain the desired treating temperature. Emulsions enter the heater treater through the inlet line, which may be located inside a heat exchanger on some units. Although this treater does not have a heat exchanger, some do. A heat exchanger is used to heat up the incoming emulsion and cool down the outgoing treated oil. This reduces the amount of heat necessary to treat the emulsion, and the cooler storage temperature minimizes vaporization and maintains a higher oil gravity. Now, this unit is designed internally to equalize gas pressure between sections. However, some units have an external gas equalizer pipe which allows gas pressure to be equalized and collected. Gas leaves the treater through a gas dome before it enters the gas outlet line. The dome is designed to remove any liquid particles entrained in the gas stream. On the gas outlet line, the gas back pressure valve maintains enough pressure in the vessel to dump liquids. The safety device may be a relief valve, rupture disc, or both. They are designed to open or burst if too much pressure builds up in the treater. Some heater treaters may have a make-up gas line with a regulator to maintain the proper operating pressure of the unit. Oil leaves the treater through the oil outlet, which is located near the top of the unit. The oil dump valve is located on the oil outlet line. This valve allows clean oil to leave the treater. Water leaves the unit through the water outlet, located on the bottom of the treater. On the water outlet line is the water dump valve, which allows water to leave the treater. In the settling section, the surface where water and oil come together is called the water-oil interface. The interface level controller maintains the water-oil interface level. A sight glass enables a pumper to see the clean oil level and water-oil interface in the treater and helps him determine if abnormal fluid levels exist. The gas-air supply line provides gas or compressed air to the interface level controller so that it can work properly. On the bottom of the heater treater are drains to empty the vessel for repairs or remove sand or clay that may have accumulated. Now let's take a look inside at the internal sections of the heater treater. A horizontal heater treater is divided into two chambers. One chamber contains the gas separation section, free water knockout section, and heating section. The other chamber contains the settling section and water draw-off section. Now let's look at each section in more detail. The gas separation section is the top section of the first chamber. This is where emulsion first enters the treater and where initial separation of gas and liquids occur. A U-shaped hood or downcomer covers the fire tube in the gas separation section. It diverts incoming emulsion to the bottom of the treater. A baffle is located between the gas separation section and heating section. It helps divert incoming emulsion to the free water knockout section. Free water settles out in the free water knockout section, which is the bottom section of the first chamber. In the water wash area, large water droplets coalesce with small water droplets and settle out. The flow spreader disperses emulsion along the total surface area of the fire tube for efficient use of heat. Emulsion gets heated in the heating section, located above the free water knockout section. As we mentioned, the firebox contains a gas-fired burner that supplies heat to the fire tube, which in turn supplies heat to the emulsion. The heating section is the part of the heater treater most susceptible to failure. To prevent undue wear of the fire tube, the lowest possible heating temperature should be used. Colder climates may require insulation around the treater to maintain proper heating temperatures. And in all climates, insulation is being used more these days to retain heat and save fuel. When leaving the heating section, emulsion flows over a weir into the second chamber. A weir is a dam-like device which maintains fluid level in the treater. In the second chamber of the horizontal heater treater is the settling section, sometimes referred to as the coalescing section. A flow spreader receives emulsion from the first chamber and disperses it along the length of the settling section for more efficient separation of oil and water. Sometimes Excelsior is used to aid in separating oil and water. The amount and type of Excelsior used depends on the emulsion being treated. Another weir is located near the top of the settling section, where clean oil flows into a clean oil accumulator box. And there the oil accumulates until it leaves the vessel through the oil outlet line. The bottom portion of the second chamber is the water draw-off section. Now, this is where the coalesced water collects until it leaves the vessel. In order to operate efficiently and safely, every horizontal heater treater is equipped with various monitoring features and several safety devices. A flame arrestor fits on the front of the firebox. Aluminum vanes disperse heat generated in the firebox to the air. This reduces the possibility of fire outside the vessel. The fuel gas scrubber prevents entrained liquids from passing into the burner along with fuel gas. Should the scrubber become filled with liquid, a float rises and shuts off a valve. This stops the flow of gas to the burner and prevents the possibility of fire. A drain valve is fitted on the scrubber to remove collected liquids. A pumper should check and drain the scrubber every day. The safety relief valve, or pop valve, is designed to open at a preset pressure level to relieve excessive pressure within the vessel. A rupture disc is a fail-safe pressure relief device. The metal disc is designed to burst at a predetermined pressure level. This pressure is usually set at or below the maximum safe working pressure of the treater. Sight glasses are the best way for a pumper to see if the treater is doing its job. Should the sight glass break, a safety feature of the sight glass valve will cause a steel ball to seat and shut off the flow. The low-level controller ensures that the fire tube is always covered with liquid. It's designed to shut down the burner if liquid falls below the desired level. Shutting down the burner keeps the fire tube from overheating, which would result in tube failure and a safety hazard. The high-level controller ensures that the vessel never becomes completely full of liquid. It's designed to shut down the lease if liquid level rises above the set point. Shutting down the lease keeps the vessel from rupturing, which would result in lost revenue, environmental pollution, and a safety hazard. In this section, we discussed the external components and internal sections of horizontal heater treaters. We also looked at various safety devices used on treaters. Now it's time again to stop the videotape, look over the material in Section 2 of your student manual, and answer the questions. I'll see you back here when you're finished. We've gone over the basics of emulsions and design of the treater. Now let's see how all this comes together. This is the third section of a three-section module covering emulsions and horizontal heater treater principles. In this final section, we'll trace the flow of an emulsion through a typical horizontal heater treater. Then we'll cover how the horizontal heater treater operates and show you how to recognize some symptoms of improper functioning. Keep in mind that most of the time, chemicals are injected into the emulsion upstream from the heater treater, so that by the time the emulsion reaches the treater, the treating process has already begun. In the gas separation section, free gas is released as emulsion splashes over the U-shaped hood or downcomer. The free gas rises to the top of the gas separation section, while emulsion flows down into the free water knockout section. At this point, most free water in the emulsion quickly settles out, and the light liquids move upward through the water, which serves as a heated wash. Water accumulates in the free water knockout section until it's removed through the water dump valve. Some treaters are designed to allow water in this section to join with the water in the water draw-off section before being removed from the unit. As emulsion rises upward through the heating section, several things happen. The fire tube heats the emulsion, which aids in the separation of oil and water. Heated emulsion rises, spills over a weir, and flows out the first chamber. Water that is separated from the emulsion settles to the free water knockout section. Gas which separates from the emulsion rises to the top of the heating section. A gas equalizer pipe allows the gas in the treater to be equalized and gathered, then removed from the vessel through the gas dome. In the settling section, three factors are at work which affect settling time. Heat reduces oil viscosity and makes it easier for water to settle out. Gravity settling causes the water to separate from the oil. And the injected chemicals help break the emulsifying agents and speed up the settling process. After passing through the settling section, clean oil spills over a weir into the clean oil accumulator box. The oil level in the accumulator box is controlled by a float. As the clean oil level rises, the float moves upward and opens the dump valve. The clean oil is removed from the treater until the oil returns to the preset level. When water separates from the oil, it settles to the water draw-off section for removal. The water-oil interface level is controlled by drawing off water from the bottom of the second chamber. The water-oil interface level is maintained by the water dump valve. As with the oil dump valve, the water dump valve opens to remove water when the interface rises above the preset level and closes when the interface returns to the preset level. Gas or compressed air is used to operate the water dump valve. An interface level controller diverts gas or compressed air to the diaphragm of the dump valve. This pressure offsets the spring tension of the diaphragm and allows the water to flow through the dump valve. When the interface returns to its preset level, the level controller vents the gas or compressed air and allows the diaphragm to seat, and the dump valve closes. The operating temperature of the heater treater will vary from lease to lease, but we should always use the lowest possible temperature to adequately heat the emulsion. In fact, in warmer climates, heating may only be necessary in colder months. The relationship of chemicals to temperature is another important factor to consider. Usually, less chemical is required to treat a warm emulsion. On the other hand, the savings in chemicals with higher temperatures may be offset by the loss of revenue caused by gravity and volume losses in the oil and increased fuel costs. Remember, the temperature controls and thermostats are an important part of any heater treater. If they don't function properly, the burner could remain off or on all the time. If it remains off, the emulsion may cool so that it does not completely break. If the burner remains on, the heater treater may overheat and be damaged. The lighter ends of the oil may be cooked off, changing gravity, and oil volume will be decreased, resulting in lost revenue. Most emulsions contain a certain amount of sludge and solids, so fire tubes should be checked periodically for corrosion, rust, and accumulation of scale. The burner flame should aim straight down the center of the fire tube. If the flame hits the fire tube directly, a hot spot will form, and the fire tube could fail prematurely. It's best for the burner to come on and burn steadily for a long period of time, rather than blasting on and off. The best flame is yellow, with just enough air to keep soot from forming. Typically, heater treaters operate under working pressures of 5 to 50 psi. The maximum working pressure for a heater treater can be found on the manufacturer's information plate attached to the treater. All parts of the treater are kept at the same pressure. The treater should be equipped with pressure relief devices capable of protecting the treater if pressure reaches an unacceptable level. For example, pressure of the natural gas used to fire the heater treater must be regulated. If pressure exceeds acceptable ranges, the thermostat could fail to close, resulting in overheating of the treater. Also, gas leaving the top of the treater is controlled by a gas back pressure valve, which controls pressure in the treater. It's important to keep treater downtime to a minimum. Here are a few troubleshooting tips. Emulsion in the lease tank indicates an improper combination of chemicals and heat. Both the chemical injector and heater treater should be checked for corrections. If neither is malfunctioning, an Excelsior pack may be used. And remember, it's also possible that the characteristics of the emulsion have changed, and a different chemical may be required. Free water in the lease tank could mean the water outlet line is plugged, or a malfunctioning water dump valve. But if the valve is operating properly, it could be a sign the treater simply can't handle the amount of free water produced. Perhaps a free water knockout unit needs to be installed upstream from the treater. One final problem to look out for is oil in the water disposal tank. There could be a number of causes. The oil outlet may be plugged, the oil dump valve might be stuck closed, or the water dump valve could be stuck open. Still another cause could be the position of the treater's oil outlet. If it's below the oil inlet on the lease tank and the back pressure valve won't hold positive pressure on the treater, oil will go through the water outlet to the water disposal tank. That brings us to a stopping point. In this section, we've traced the flow of emulsion in the heater treater and gone over safety devices and troubleshooting tips. This also completes the module, Emulsions and Horizontal Heater Treater Principles. I hope you've become more familiar with design and operation of a horizontal heater treater, as well as the basics of emulsions. Take some time now to stop the videotape, fill in the blanks, and answer the questions in Section 3 of your student manual. Good luck, and I'll see you next time.